This is the programming module for CIS121 Computer Concepts 2 at Portland Community College. My name is Al Zimmerman. In this first week, we're going to do an overview of programming, how to set up your head like a programmer, how to diagram and specify programs, and do a quick overview of all the variety of computer languages that are out there. In this presentation, we're going to cover that idea of how to think like a programmer. This will help you get your head around it if you're just starting, or it'll help you optimize your thinking if you've been programming for a while. Then we're going to look at specifying programs, both as diagrams and as simple English statements. And finally, we're going to do an overview of the different types of programming languages so that you'll have a chance to get a bird's eye picture of the world of programming. First, let's talk about thinking like a programmer. The essential difference that programming brings is that instead of painting a painting, you have to write down the instructions, and then somebody else, a well-meaning idiot, goes ahead and tries to paint your painting for you. Another analogy is, instead of baking a cake, you write down a very detailed recipe, and then you hand that recipe off to somebody else, and they follow it step by step. There's no intuition, there's no tacit understanding, there's no common sense. So if you're the kind of hands-on person that has done crafts or graphic design or that sort of thing before, you're going to find yourself stepping back, and it can be a little frustrating, stepping back and having someone else do your actual work for you. The plus side is software can do so much. It can do so much more than we can do with our hands or with our own single individual effort. And you'll see that as we go along. There's other aspects to thinking like a programmer that will help you get better at programming. The first thing is, before you start writing your code, know exactly what you want. Have it clear in your mind, have it specified clearly so that you know what you're building. You know what your customers want. The second tip, if you will, is to narrow your focus to the smallest possible piece. There's two aspects of this. One, if you're building a system with a lot of features, just cut it down to one or two features and build those. Analyze them, design them, build them, and then show them to customers. If you do this over and over, it's called iterative development. And each time you can develop a small part of the system and make sure that you are doing it right. The other aspect of this idea of narrowing your focus is think about things in very small pieces. Focus intensely on just the routine you're writing. Think about making this routine do just one thing well. Don't try to cram too much into a program or into a system. You have to learn different programming languages. You learn a new one every year practically. And there are many similarities between languages, and there are differences. Some languages are better than others. But just get used to the idea that you're going to learn a new language, and you're going to do it fairly often. It's fun and easy once you learn your first language. It's easy to learn a second language, and after that it becomes just part of what you do. The most important tip is to be precise. Every character counts. Every single line can be a point of failure. And some languages, like JavaScript, when you get it wrong, not only do they not complain, they don't do anything. It just falls over dead and you have no idea what's going on. So be obsessive. Check every character. Before you run that program, check every error message that you get and only work on that one error message. It's an aspect of narrowing your focus too. Just work on one thing at a time and make sure it's right. Now let's talk about specifying programs. There are two main ways of doing specifications. One, you can draw diagrams. People really understand diagrams quickly. And you write English specifications. In our case, it's English. It's your native language. We're going to talk about a method of using very simple language to specify programs, and you'll get a chance to try these out in your assignment. So first of all, let's look at diagrams. Flowcharts are a fairly old diagramming technique. I think they've been around since 1920 or something like that. But they are not obsolete. Almost everybody understands what a flowchart is. Now we're only going to look at 2 or 3 or 4 different kinds of symbols. We're going to use a very restricted syntax for our diagrams. Let's take a close look at that. First, the most elemental part of a flowchart is the step. It's a process step. It's a rectangle. You go in. Let me see if I have a pointer here. You go in and flow comes down here. There's one operation which is described in the text inside the rectangle, and then flow continues out there. There's no stopping. There's no decisions. We use a rectangle shape. And what you actually make this rectangle do depends on the situation. We'll talk about that more later on in this presentation and in a second presentation about how to create procedural flowcharts. The second kind of symbol that you'll see is a decision diamond. Now this is a place where your control flow comes in, and then you ask a very simple yes or no question. And if it's yes, control flows out that way. If it's no, control flows out the other way. One way in, 2 ways out. Now this question has to be a simple yes-no question. The answer to the question is either true or false. Now it's true that there are some questions that are not this simple. But you can set up a program so that it checks one aspect of the situation, then it checks another aspect, then it checks another one. So you can break down these more complex questions into simple series of yes-no questions. Usually you write the question inside the diamond, but for complicated questions you can put it outside. The other thing you'll see on every flowchart is the starting point and the ending point. These are called terminators. Usually a program starts when you double-click on it or when you start the computer. But sometimes the program starts when there's some sort of event, when you click on a link or when you press a button. Then the program starts here and it flows downward. When everything is done and all the decisions have been made and all the steps have been accomplished, programs always end at a stop terminator. These are simple circles. Now there are more complicated modeling languages, diagramming types. One is the Unified modeling language. It's a large set of different kinds of diagrams. They can be very precise. They can allow you to completely specify some software down to the last detail. And these kinds of drawings, UML drawings, are very useful for other engineers and technologists. They're not so useful for talking to customers, though. My experience has been you have to spend so much time explaining what the diagram means that they lose interest. So flowcharts are a great way for you to communicate with your customers. Now here are some guidelines. Only put enough detail in the diagram to get across your point, to communicate effectively with your particular audience. If you're talking to customers, make the steps things they understand. If you're talking to other programmers, make the steps at a level of detail that they find useful. And at all times, leave out the details you don't need to talk about. The customers don't need any extra detail, it just confuses them. And programmers, especially people who are good with the particular technologies and languages that you're using, will fill in the details themselves. Now, in our exercises, we'll be actually flowcharting a program down to the code level, and you'll see steps that are like n becomes n plus 1. But that's not typical. Typically, you'll see flowcharts at a higher level. We're doing it in that very basic way for this class so that you can make the association between flowchart symbols and the actual lines in the program. So we've looked at doing flowcharts or diagramming processes. Let's take a quick look at pseudocode. Now, pseudocode is just using your native language, in my case English, but using a very restricted vocabulary, very simple sentence structures, and saying do this, do that, use this, making it as simple as possible and constraining yourself to allow you to express what the program is going to do in your customer's word. Again, you just put in enough detail to get the meaning across. Now, sometimes people actually take the pseudocode they write, the little process descriptions, and they put them in the program file as comments. And then as you construct the code using the programming language, you can see your specification there as comments, and you can make sure that they match. These days, there's a new development. Well, it's a couple years old, and it's called Cucumber. The tool is basically a way to take these simple English descriptions of how a program should work and transform it into actual testing programs. So this allows you to say, this is how the program should run, and then actually take that specification and verify that the program actually does that. For example, let's say you had a web page and your specification was, well, when you open this URL, the page should have the word sign up on it. When you fill in the form with your name and you click the submit button, then the page should change and it should say welcome. You can write a simple little pseudocode procedure just like you see here on this screen. And then you can take it and actually turn it directly into a test program and verify that your program actually does what you specified. Now, we won't have time in this class to take a look at this, but when you get out there, if you're doing programming in your career, you'll see that a lot of people are starting to adopt this method of making sure they've got high quality software. Now let's take a look at computer languages. Short overview. There's a hierarchy of languages, extending from the very simple machine code down to assembly code, to procedural languages, object-oriented languages, and then graphical languages. We actually draw a picture, and the program executes. At machine code, it's actually the bits, the ones and zeros, that the computer interprets and executes directly. It is machine language. It's unique for each architecture. So the machine code on an Intel processor, for example, will not execute on an ARM processor, the kind you would find in a phone. It's very concrete, it's very detail-oriented. At the other end of the spectrum, you see languages that are set up to deal with abstract concepts. Things like, accounting. Languages that can directly express complicated things like sets and iterating through sets. These languages up at that end of the spectrum are understandable by humans. They think the way we think. If you think about a team of people, each person on the team has their own responsibilities. Well, that's like object-oriented program. Each object has its own responsibilities, knows what it's supposed to do. At the other end of the spectrum, the languages are very quickly understandable by machines, and it's difficult for a human to write in those languages. You get a good payoff. If you can write an assembly code, you can end up with very efficient, very fast code. Let's take a look at some examples. Now this is what machine code looks like. This is old Windows code. And it's actually hexadecimal numbers. You can see them here. Here's the addresses in memory where this code is. Some of the code is actually text. Some of it isn't. It's operators and operands, that sort of thing. Now if you take this machine code and you add symbols to it, you get assembly code. You can see the machine code is still here. Here's the locations in memory. But now we've made symbols that tell us, well, this is a move operation, this is a subtraction operation. Here are registers. You can see the registers here. Those are things that store numbers. This is kind of hard to understand, but the other side of it is it's very simple. It's a machine after all. I think over the years I've learned probably a half dozen to a dozen different assemblers. And it can be very, very difficult to learn a particular assembler. You go up the spectrum to procedural languages and things get easier. Here, for example, is JavaScript. Now you can see that we can use real English words to name the variables. We can do things like create functions that have words in them that are a set of instructions that are easy to call. We can use real names. We can use real strings when we're setting up arrays of things. And we can call functions to make it real easy to tell the computer what to do. If you go to the next step, we're looking at object-oriented languages. Now, if you look at the code itself, this happens to be C#. It looks very similar to that procedural language snippet we just saw. And that's because inside each object there are methods. There are little programs that run and actually implement what that object knows how to do. Those are just procedural programs. And it's the same kind of language. Many procedural programs like C, C#, JavaScript, Java, they're based from the same kind of heritage. In the same way that many human languages are based on Latin or are based on different Asian roots. But object-oriented programming is much more than that. Here's a simple diagram that gives you an idea. For each object, there are these software methods that we just mentioned, and there can be a number of them for each object. These are the things that that object knows how to do. And then each object has its own information that it keeps private to itself. It's the sort of thing that it knows, and it knows what to do with. The other interesting thing about object-oriented programming is inheritance. You can have one kind of object, say, an office worker. And an office worker knows how to read email and how to use the telephone and has other methods that it knows how to do. And then you can get a specific form of office worker, say an accountant. Now, an accountant knows how to do everything that an office worker does. They can exist in an office, they can talk with their peers and call people and use email. But they also know how to do sums and how to do invoices and do things that are unique to accountants. So, inheritance is a very powerful way to reuse code. Writing software is hard. Writing software is error-prone. So when you get software that works well, you try and reuse it as much as you can. And object-oriented programs with inheritance make that very easy and quite intuitive. Finally, there's graphical languages. Now, these are used both by engineers and scientists who don't want to actually go into the details of programming even though they're capable of it. They're also used by children to learn programming. This particular graphical language is called LabVIEW, and it's used by people who are modeling systems or creating systems that it takes data from a COM port, applies different internal data. Each one of these boxes represents a little snippet of software that does something, takes these inputs along these wires, transforms them, and then outputs them back into the real world. This is LabVIEW. It's used by scientists and engineers. If you have a Lego set, a Mindstorm set at home, they use a graphic language that even little kids can understand. Many kids learn how to program using a language called Scratch, which also has a graphical element. In any case, we've got all of these different types of languages stretching from the very simple, very machine-oriented code down to the graphical code. In this class, we're going to take a quick look at a language called JavaScript, which is largely a procedural language, although it has some object-oriented aspects to it. It's not a pure object-oriented language like Ruby or Smalltalk, but goes away in that direction. So that's the end of this particular screencast. I'd like to invite you to go to the next screencast, whatever's in the module, read the assignments, and read the materials, and then try out a flowchart of your own. Thanks.